So we continue our discussion of symmetry groups acting on sets by defining some new concepts: stabilizers, stabilizer subgroups, and fixed point sets. So just to give you a preliminary idea, stabilizer means something that doesn't change something. All right? So stabilizers are going to be group elements that don't change various points in the set X. Stabilizer subgroups will be a set of stabilizers that actually form a subgroup of the group G. And fixed point sets are related to these two. So let's go and look at this discussion. So every rotation of a cube has an axis of rotation as well as an angle. For rotations which are symmetries, we've considered three possible axes passing through opposite pairs of faces. Okay, so we have the axis through x plus x minus. So you can take a cube in your hand and follow along with this. You know you've got three pairs of opposite faces. There's x plus x minus, y plus y minus, z plus z minus. Let's take x plus x minus and consider the set of all rotational symmetries having this axis. In fact, this set of symmetries forms a subgroup of the symmetries of the cube. In this case, the subgroup is isomorphic to the rotations of the square. So can you see that? Well, let me go through the paragraph and we'll discuss this whole paragraph. Now, all the elements in this subgroup leave the face x plus fixed. Although x plus rotates, it remains in the same place. Similarly, the rotations about the axis through y plus and y minus form a subgroup whose elements leave y plus fixed, and the rotations about the axis through z plus and z minus behave the same way for z plus. All right, so let's go back to our cube and see what we're talking about. Here's my x-axis. If I rotate around this axis, then this face here, this square face, always goes to itself. So we can say this square face is stabilized by all of the rotations about the x-axis. The paragraph also mentioned that the rotations about the x-axis form a subgroup, because it's just like you're rotating a square. It's a subgroup with four elements: the identity, 90, 180, and 270 degree rotations about the x-axis. And notice that the same thing it does to the front face, it also does to the back face. So in fact, that group stabilizes both the front face and the back face. Now you could say similar things about the rotations about y and the rotations about z. So that's what that paragraph is saying. So our general definition is, given that x is a G set, so like x is a generalization of the cube and G set is a generalization of the rotations. So given that x is a G set, and take any element in x, we let G sub x be the set of group elements that fix x. In other words, Gx equals x. And Gx is called the stabilizer subgroup or isotropy subgroup of x. All right, so in terms of the example that we just talked about, the group of rotations around the x-axis are the stabilizer subgroup for the face x plus. They're also the stabilizer subgroup for the face x minus. Okay? Now, we haven't actually proven that this set of group elements is a subgroup. That's exercise 13.2.9. You can prove that any set of group elements that fix a particular point in X will form a subgroup. So that's your exercise here. All right, now let's look at this from another point of view. We've talked about elements of the group G that leave a particular element of the set fixed. We can turn this around and consider elements of X which are fixed by a particular element of G. In fact, each element of G has an associated subset of X that it leaves unchanged. All right. So I can do, for example, using our same example back here, if I take this face, then the set of rotations, four rotations that we talked about, is the stabilizer subgroup for that face. But on the other hand, I can consider this rotation of 90 degrees about the x-axis and think about what points in the set X are stabilized by that 90-degree rotation. So what points in the set X are stabilized by that 90-degree rotation about the axis X? Well, if you think about it, the front face and the back face are stabilized. Everything else moves. For instance, this edge moves to this edge, this corner moves to this corner, and so on. All right. So the notation is here. The fixed point set of a group element is the set of group elements which are not changed. I'm sorry, is a set of points in the set that are not changed by the group element. And here's several examples to work through so you can understand these concepts. Examples and exercises. And I think that's all I'll talk about that. Give you a chance to work through those exercises yourself.